Okay, so every time. We are going to talk about neuromuscular adaptations. And this is actually the last lecture in our first unit. And so as we're going through this, this really kind of concludes the first week of class. It's all so expedited in the summer. So what are we going to learn? We are going to learn how the body adapts to strength training via neuromuscular adaptations. So when we talk about the interaction of 6 factors that develop and help maintain muscle mass, there are a few key terms that should come to mind. So we've talked about a few of these as kind of reoccurring concepts, but the first is going to be genetics. So genetics definitely plays a role into how we develop and maintain muscle mass. Your exercise status also makes a difference. Have you been sedentary? Are you active? Where are you actually in your training status, and how will that lead to help maintaining and developing muscle mass? Nutrition is also a key factor. Gender and hormones will also play a role. Age and nervous system activation. We talked about kind of that fight or flight or reaction time. And so nervous system activation also plays a role. The final one, and there's many, but the ones that I'd like to talk about are going to be those environmental factors like sleep, sleep, nutrition, a lot of them sort of tied together. So these are 6 factors that interact that help to develop and maintain muscle mass. Okay, so we're going to spend a little bit of time on this graph. And this graph is really important when talking about neuromuscular adaptations to strength training. So again, we've got time here on our x-axis, and then we have improvement here on our y-axis. So let's spend some time and really break down what's happening. So typically in training studies usually last about 10 to 12 weeks. And the reason that happens is because those doing training studies, not always, but more than not, are faculty, are professors at a college. And what is a typical, not summer, but what's a typical semester length? 10 to 12 weeks, right? So this is where we have that 10 to 12 week training studies. And then we have long-term strength training. And this can be, let's say, 3 months to years. And then now typically elite athletes have been training for years plus. Sometimes phenoms that are a little bit younger, not so much. But generally speaking, our training studies last about 10 to 12 weeks. Our long-term strength training gains will be between that 3 month to years mark. And then elite athletes and those that have been at it for a really long time have been training for years plus. So let's go ahead and look at our muscle mass or our hypertrophy. You can see that in those first 10 to 12 weeks, we do not have a lot of strength gains, if you will. We start to see more hypertrophy and muscle mass increase throughout the long-term studies. And then it really does sort of plateau once you hit that elite status. Now, neural adaptations are a little bit of a different story where we have really big increases in neural adaptations in the first few weeks of training. And they tend to kind of plateau and not really account for much in our strength changes after the initial training. And I'll expand on that in just a second. And then our strength changes are really going to be apparent early in a training program, and they'll continue to get bigger as we go through the months and the years, and then plateau again off whenever we get to our elite status. So I want to write a little bit over here on the left-hand side. So if you're writing with me, give yourself some space. So in training studies, I'll make this red. So in training studies, meaning this first 10 to 12 weeks, neural adaptations are really prevalent. And this is because it's related to learning. Think about how intimidating it is to walk into a gym for the first time and you have no idea how to use these equipment. You have no idea what proper form is. You're really learning. And so that's why neural adaptations are so prevalent in the beginning of a training program, because you are learning the movements, you are learning coordination, and you are learning molecularly the ability to recruit prime movers. So this learning, these neural adaptations, all of these play a really big role in strength training development. Strength training development. So then obviously neural adaptations are not going to account for strength changes as we get into the months and the years, because your body already knows proper coordination. It already has the ability to recruit these prime movers. It already has the coordination to do whatever the movement is that you're doing. And then so whenever you get into elite status, again, things are just going to sort of plateau where you're kind of as good as you're going to be, and you're really trying to maintain those gains that you have acquired. So in long-term studies, the size, so I'm going to say over here, long-term studies, we're going to have the size. So that's muscle mass, that's hypertrophy. So the size of our prime movers will play a major role in strength development as the years go on. So really be familiar with this graph, understanding that neural adaptations and strength changes happen really quickly and dramatically in the beginning, whereas muscle mass and hypertrophy take a little bit of time before you start to see those bigger gains, if you will. So early in a training program, the portions of gains and strength that occurs with training is largely due to neural adaptations, not the enlargement of the muscle, which is going to come later. So what are these adaptations? So we have improved synchronization of motor unit firing. So this really helps with that neuromuscular control, being able to understand whenever that impulse reaches the neuromuscular junction, how your body is able to respond to that. And then we also have improved ability to recruit motor units. So this plays a really big factor with these neural adaptations. So fiber types and motor unit recruitment, you'll get a little bit into this in the first homework. So if you are more of a long distance runner, you have more of these type 1 slow twitch fibers. So this is somebody that really thrives at those events that are over 3 minutes. So we're talking 5K to a marathon. And then If you have type 2A, that's when you're at that 50% anaerobic, 50% aerobic. So you really have this fast twitch oxidative. And then your fatigue rate as you get to the type 2 fast glycolytic, those are going to be short sprints. So that's your 10 seconds, to 30, let's say 30 seconds. You will have type 2, which you will have a very high fatigue rate. You can't keep up that high intensity for very long. So over here, I have motor unit recruitment is the activation of additional motor units to accomplish an increase in contractile strength of a muscle. The motor unit consists of a motor neuron and all the muscle fibers it stimulates. So we're trying to tie in a few of these concepts that we've talked about in this first week. So for our motor unit recruitment, the example that I really like to use is that and this is so important. Sometimes students don't quite grasp this concept, so I'm really hoping that you'll remember this. So regardless of the load being moved, slow type 1 fibers are always recruited first. So how I want to explain this is my iPad, sorry, I've recorded a lot of these today. I'm like, so my iPad pencil here. If this is laying on my desk and I go to pick it up, you know how you go to pick up something and you think it's heavier than it is and you kind of get off balance? The point is that you will always recruit slow fibers first, whether or not you're picking up a pencil or you're picking up a piano. So let's pick up a pencil or your fast fatigable, pick up a piano. Okay, so or a 10-pound weight versus a 45-pound weight. You will always recruit slow fibers, type 1 fibers first. With the increasing force required, then you will go to type 2A, and then you will go to type 2X and type 2B. So the body does not want to waste energy. It only recruits motor units as it needs to move the load. So even if you go to pick up a piano, you're going to go through your slow twitch first to get to those fast fatigable. So the body does not want to waste energy. It's only going to recruit as many motor units as it needs to move the load, but regardless of the load, it will always recruit those type 1 slow muscle fibers first. So this is just sort of another visual and a way to look at this. So this is looking at motor units and how they kind of differ with this threshold. So let's just look at the first part here as to not to confuse yourself. So we have time. Remember to orient yourself on the x-axis in seconds. And then you have your force percentage rate on the y-axis. So if you are picking up a pencil, you are going to be recruiting these low threshold. So low threshold need a low force, a weak neural drive. Picking up a pencil is a weak neural drive. You do not need to recruit your fast twitch glycolytic recruitment to pick up a pencil. Now, if you are picking up a piano right here, you will need a high force to produce when a large number of motor units are activated, because picking up a piano is a lot harder, a lot more strenuous than picking up a pencil. So if this graph doesn't jive quite with how you think, don't worry about it. The whole point is to understand recruitment, that you will recruit those slow fibers, those type 1s, regardless of what you're picking up. But whenever you pick up a pencil, you need a weak neural drive. It doesn't take a lot to pick up this pencil, but it does to pick up a 50-pound dumbbell, a 70-pound dumbbell, a piano. It will take a higher force to be produced to activate those motor units. So, when we talk about adaptations to strength training, we know that the neural adaptations are most prevalent in those first 8 to 12 weeks. I've stated this, but that's because of increased coordination, increased motor unit recruitment, increased coordination of those motor units, and then these inhibitions, these GTOs and muscle spindles. We'll talk about that in this 3 slides. But I do want to just again kind of give a little bit of a different visual for this muscular strength response curve. So again, muscle hypertrophy is going to be much stronger towards the end of that first training cycle, whereas neural adaptation will be high in the beginning and then sort of drop off. This really is just a different way to visualize what's going on here. If you understand this graph, don't get so worked up into what this graph is showing, but just know that neural adaptations are high in the very beginning, whereas muscle hypertrophy is low, and they sort of crisscross as we go through that training. I shouldn't have used pink on pink, but I'm sorry about that. So our neuromuscular adaptations to exercise, we've talked about this. Hypertrophy is the process that involves an increase in the synthesis of contractile proteins, actin and myosin. We've talked about that within the myofibril, and an increase in the number of myofibrils within a muscle fiber. So the new myofilaments are added to the external layers, resulting in the increase in the diameter. So that is why hypertrophy really does take weeks to months to actually get. So the Golgi tendon organ, the GTO, that's what I mean here, the Golgi tendon organ. So the Golgi tendon organ is a fine-tuned sensory receptor. So it detects tension applied to a tendon. And so it responds to a feedback mechanism so that a muscle doesn't stretch too far. So it really helps during exercise when a muscle is contracting or stretching. So these Golgi tendon organs really are there so you don't stretch past the point that your body is able. That's when you get pulls and tendon pulls, and that's when you can become injured if the Golgi tendon is not quite operating and doesn't have the proper neural feedback to help with it. The final thought I want to introduce is this idea of proprioception. So the brain receives and interprets information from multiple inputs. So we have our vestibular organs in the inner ear, we have our eyes, we have our stretch receptors. And so proprioception really is your awareness in time and space. So if you balance on one leg, that's easy-ish. If you close your eyes, it's harder because you're taking away the eyes to send visual information to help you balance. And so proprioception is something that we really use a lot when we're rehabbing individuals that have had a stroke or who are just older and have sort of lost some of that motor control and that motor function. So training the proprioception organs and body is really, really important. So we've talked about 6 neural adaptations to strength training. We have a greater efficiency in neural recruitment patterns. We have an increased motor neuron excitability. We have increased central nervous system activation. We have improved motor unit synchronization, lowering of these neural inhibitory reflexes, and inhibition of Golgi tendons. And so that concludes Unit 1. We did it. Okay, see ya on the next one.